This Week in Radio Tech, episode 183, is brought to you by Axia Audio and the workhorse Axia Element Audio Console. Watch the Axia installation video and find out more at axiaaudio.com.
And now, our feature presentation.
Twert.
X192 is now official as AES67. Is this important? Well, if you're an engineer working with audio, it sure is.
All right, calm down. He says that to everyone.
This calls for immediate discussion.
What's up, Doc?
All your days are belong to us.
From his palatial office of important business,
or in a choice hotel in a distant land,
this is Kirk Harnack.
Chris Tobin joins me and our guest, Greg Shay. Greg literally helped write the spec for AES67.
You're dialed in to This Week in Radio Tech.
Hey, and welcome into This Week in Radio Tech. I'm Kirk Harnack, your host. I'm glad you're here. I'm glad you're here every week. We've got a special edition of This Week in Radio Tech for you. We're recording it at a different time. So if you're watching live, welcome in. Glad you're here. If you're listening or watching on a delayed basis, well, we shot the show, about 8 hours earlier, 9 hours earlier than usual because of some scheduling conflicts. But it's very appropriate. We have got some fantastic topical news to talk about. It has to do with a standard for getting different IP audio systems to talk to each other. And our guest, I'll introduce him in a minute. It's going to be Greg Shay. But first of all, let me bring in our co-host, a man who knows all about IP and how to make these things talk at least to themselves. And that's Chris Tobin, the best-dressed engineer in radio. Hey, Chris, welcome in.
Thanks, Kirk. Yeah, I can make them talk to themselves real easy. The two words, loop back. Yeah. I'm with the folks at CCS Music Cam. We do IP audio and IP video, and we too will be looking at the AES67 standard and make things happen like everyone else.
And that is the big news. And you gave your disclosure. I'll give mine. I do work for the folks at the Telos Alliance, including Axia, the inventors of Livewire IP audio. And our show is sponsored, thankfully, by the folks at the Telos Alliance. I appreciate that. But hey, other sponsors are welcome. Just contact the GFQ network, and you can get your message out to all the engineers who watch and listen and download this podcast. Thousands of them all around the world. Think about that. All right, let's bring in our guest. Our guest on this show is a guy who I've known for some years now. And, I didn't ask him if it was okay if I introduced him this way, but one of the cool things I found about this guy is the inventor of the world's coolest, most efficient, most perfect FM stereo generator algorithm. And so we'll have him talk about that in a minute. Ladies and gentlemen, it's Greg Shay, the Chief Science Officer for the Telos Alliance. Hi, Greg. Welcome in.
How you doing, Kirk?
Good. Glad you're here. So,
good to be here.
On that introduction, we're going to get to this interesting topic of one packet to bind them, so to speak, an interoperability standard for IP audio studio systems. But I touched on this thing about how you got involved with our company, Telos, and at the time Omnia. You were talking to some folks there about designing a stereo generator, and you've got something that's pretty unique here and in use at literally over 10,000, maybe over 20,000 radio stations around the world. Tell us about this stereo generator.
Sure. Well, the story is that when you're an engineer in a city, so here in Cleveland, you kind of want to know who's doing, cool stuff around that you might want to work with someday. I had been working for a video codec company, and I was actually out at NAB, and I ran across, here was this company called Telos in their trade show booth, and they're from Cleveland, which is, of course, my hometown. So I thought I ought to get to know these guys someday, and so the opportunity came up, and I went down and talked with Frank and Steve and saw if there's any way we could work together. And it turned out that this was during the late development of the Omnia 3, and it had 14 DSPs, and they were down and only had one left. And they needed the stereo generator written, which they had never done before, and they didn't know if it was going to fit, and they said, would I like to have a crack at it?
Prior to that, the stereo generator had been accomplished in standard hardware with, I guess, analog circuitry, which is how it had been done for decades up to that point.
Right.
And by the way, I should set the stage. The stereo generator in an FM processor is the thing that takes the left audio and the right audio that has been processed and limited and maybe even clipped, and takes that left and right audio, which are now separate, left audio, right audio, two separate analog or maybe digital streams, and puts them together into a standard format used around the world called the FM multiplex or FM baseband. And this is where you have left plus right and the stereo pilot signal and the left minus right. And you put this out as what we call stereo baseband or FM multiplex. And this is what actually gets transmitted over the air so that mono radios can hear it okay and play mono, and stereo radios recognize that, this is in stereo, I'll grab this other information and demultiplex it back into left and right for your speakers. So, sorry, Greg, go ahead.
All right, good. So I knew that to make a precision, the stereo multiplex encoder started with a couple of fundamental things, and this is what I jumped into. And of course, the context of this, I'm trying to impress these guys. So, I'm really trying to do a good job, put my best foot forward.
You're looking for a job at this point. You're looking to get hired.
I have this philosophy that it never hurts to have, irons in the fire. And, these were cool guys, and I wanted to get to know them. So at that particular moment, I wasn't looking for a job, which is part of the story, too, a little later. For instance, just a technical tidbit about that stereo generator, it turns out that the more accurate and mathematically precise that you can generate the sine wave, which is the carrier of the pilot of the stereo multiplex, the more accurate and clean the resulting multiplex will be.
Oh.
So I actually did a couple of different precision sine wave generators, and this had come from, I had fooled around with computer graphics, and if you know anything about the mathematics, it's the same thing as drawing a circle. So essentially this is a precision circle generator. And I had a simulator, and I was particularly good at designing filters, and I had it all simulated and everything working. And so basically the very first delivery that I handed over to Frank, I thought was going to work, but I didn't know if it was everything that he wanted. So Frank fires it up, he turns it on, and he was really impressed. It really worked well. In fact, there was some tweaking. Frank then proceeded, now that we could do that, to do some upsampling for the clipping that was done in there, and so it really turned into a real nice result. And then they really wanted to hire me. So that's the rest of that story. So that sort of is a really good way to impress your new future boss, is do a nice piece of work for him. So about 6 months later, I was hired on. So that's how that happened to be.
So this stereo generator that's in use in all or virtually all modern Omnia processors, it just does a fabulous job of making very clean stereo multiplex baseband. Is that what I would take away from your design?
Right, and that comes from, I used the full extent of the precision, of the DSP to make that. I would say lesson learned in design of a stereo generator: start with an extremely clean sine wave, and then go from there, and keep all your filters good.
By the way, just to help me understand, what defines a clean sine wave? No noise, jitter. What's clean?
Right. To the limits of the precision, of the numerical precision of the calculations that, and you can check it with the fast Fourier transform of the sine wave. So for the 24-bit math that's in that product, the side lobes are down like 140 dB. So it's very clean.
Oh yeah, wow. Okay, that's a lot down. Okay. Cool. All right. Well, let's move on to the subject at hand, and I'm going to take the liberty of doing just a tad bit of reading to bring us all up on the same page here. Those of you who know me or know Chris Tobin, we've both got experience with Axia's Livewire. Of course, I work for the company, and Livewire is this standard. It's a collection of existing standards plus a little bit of magic to transport very high quality audio over a computer network within a studio or an enterprise environment. And the idea there, it's got to be very low latency, very, very low latency, as low as it can possibly be, so that when a disc jockey talks into a microphone and the audio gets digitized and routed around through the computer network and makes its way back to a headphone output where it gets turned back into analog and goes through a headphone amp and into the disc jockey's headphones, that whole round trip, it's really best if it takes under 3 or 4 milliseconds going through the computer network. And before Livewire came along, there was no way to get that done. Nothing off the shelf, certainly, and nothing that we knew of that had been prior invented. And so some really smart people in the U.S. and in Latvia worked on this problem of getting the latency down to where it was acceptable, to where when you talk in the mic, you didn't hear yourself back as kind of a comb filter effect, or worse yet, even an echo. I mean, at the time, there were things like CobraNet, and I'm not sure if EtherSound had come along yet, but these had way too much latency to use. So let me just give a so now we have all these different silos. These different companies have different IP audio standards, and some of them work very well. Some work pretty well. But they all intended, for this kind of live studio usage, like Livewire was invented for. So here's just a summary of information that will help us start on the same page for this discussion. High performance media networks support professional quality audio. We're pro quality, we mean 16 bits of digital bit depth and at 44.1 kilohertz sampling or higher. So basically, we're starting with CD quality, and it can get better from that as part of the standard, but the minimum is CD quality, uncompressed. With low latencies, AES is saying less than 10 milliseconds. Okay, fine. Upwards of 10 milliseconds does get to be noticeable in your ear, but it's got to be less than 10 milliseconds and compatible with the live sound reinforcement environment where you are worried about phasing in speaker arrays at different places. The level of network performance needed to meet these requirements is available now on local area networks. Well, we've known that for 10 years, and is achievable on enterprise scale networks, but generally not available on wide area networks and certainly not the public internet. So the gear you need to do this, you can assemble, you can do yourself like we've been doing for 10 years at Axia, but you can't do this kind of thing over the public internet. The most recent generation of these media networks use a diversity of proprietary and standard protocols. Despite the common basis in Internet Protocol, or IP, these systems don't interoperate. So Wheatnet can't talk to Livewire, can't talk to Dante, can't talk to Ravenna directly. Well, actually it can now, but at first couldn't. The standard we're going to talk about, called AES67, provides specific recommendations for interoperability. The standard focuses on defining how existing protocols are used to create an interoperable system, and no new protocols have been developed to achieve this. The standard is expected to be useful for commercial audio applications, including fixed and touring live sound reinforcement, so in addition to radio studios. It's also useful for distribution in broadcast, music production, and post-production facilities. So the standard should cover lots of folks' needs. Now, with that introduction, so we're all kind of on the same page here, Greg, where do you suggest we start this discussion about this standard AES67?
Sure. Our timing today is quite extraordinary. When we were talking about setting up this show for today in this subject, which was just a week ago, AES67 was still in the future. And, we called it X192, which was when a subcommittee is working, you get an X number. But yesterday, AES67 finished its 6-week public comment period and was published. So this is very timely. We couldn't have planned it any better.
Yeah. It hit all the news. Radio World, if you're an engineer and you get Radio World, you saw these announcements come out. And I happen to get some from other sources too. But so, yeah, very, very timely. And you mentioned X192. This was a committee formed. I think you and Telos were a founding member of this committee to get the conversation going amongst manufacturers about a standard.
Yes. Maybe it'll help to explain a little bit of the process of how the AES works. Basically, anybody can come forward and make a proposal to try to do something. And once you organize that, the AES will give you one of these X numbers. So we were X192. The particular form that we took was we had a expert in the group, and that was Kevin Gross, who is was the inventor of CobraNet, and he led the group. And basically, through the committee and through Kevin's writing of the document, that then gets submitted for review, and the AES then puts their blessing on it. So that's kind of the process. That took about 2 years. It started about 2 years ago, and we were interested. Axia Telos Axia was interested from the beginning, and even initiated a little bit by Steve Church. So came right from the source on our side.
Hey, I guess we should back up and lay one more piece of groundwork. Why is it that that there are these incompatible systems? I mean, either philosophically or practically, why does it work out that way? That, well, it's maybe the same answer, why a Ford engine doesn't fit into a Chevy. But why doesn't Livewire work with Wheatnet? Even though they're both using RTP, they're both using real Ethernet connections, why don't these and Dante and Ravenna naturally and others just talk to each other?
Well, it turns out that many of these systems, even though they're based on, as Livewire is, a standard like the IETF, what's called the RTP, Real-Time Protocol for audio streaming, and we chose what's called L24, which means linear 24-bit audio, there's still enough details about how you go about doing this that can make systems incompatible. So one of the things that we did with Livewire from the very early days, so this goes back more than 10 years ago, we found where we could other devices, including software. So one of the very first ones we had was the QuickTime player from Apple. And Apple, the QuickTime player, could play RTP streams at L24. And so one of our tests that we did was made sure that we could play a Livewire stream through the QuickTime player. And for instance, the missing link there was no real specification about synchronization. And of course, a software app on a PC may or may not, back in those days in internet streaming, may or may not actually synchronize. They accepted typical internet audio streaming behavior at the time was, your buffer might reset itself, every couple of minutes. And
okay.
That was not acceptable for professional use, but was fine for internet streaming. So
yeah.
So the answer to that is the devil's in the details, and all you need is one detail different, and then it doesn't work.
So, what's the motivation for different companies to talk to each other? I mean, a practical example. Why would Axia want to be in some way compatible with Dante or Wheatnet or Ravenna? Why would wouldn't companies want to keep customers in their own on their own playground?
Well, I think I remember it most clearly being said by Steve. It's the IBM PC model that if there is commonality, if you have a standard or a de facto standard that there's a common ground where people work together, the whole industry is more successful, and even though you have a piece of the pie, it's a much bigger pie. So it's basically that theory. We believe that it was such a fundamental change and going to be the future of how things are done that we know we make products, codecs, mixing consoles, audio processors, all these various things. Our fate does not hinge on our audio networking standard. So from our point of view, it's better for the radio industry and the audio industry to be this more healthy, and off we go, and then we carve out our piece of it.
So things, it does seem then things that don't work together can prevent people from upgrading their equipment because they don't work together, or they realize they had to get a Telos phone system to work with a Wheatstone console. We have to buy some extra stuff to connect the two together. Gee, why don't they just plug into each other? And so if we remove that barrier, then people are more likely to buy what they want based on the merits of the gear and not the merits of the interconnecting technology.
Yeah, that's a fair statement. The other aspect of this is the users, the customers, are always going to want a standard. It usually does happen sooner or later. And are you going to try to stand in the way of that ultimate inertia and freight train? So,
sure.
It's one of these things. They say standards are something that are good for the users, not so good for manufacturers who are trying to monopolize something. But at the end of the day, you can't hold that wave back.
And I guess that for some time, ever since its inception, the folks at Axia and Livewire have worked to make that a standard by getting connected, by partnering up with other companies. So there's dozens of companies that have gear that works with Livewire, but same thing for for the other manufacturers. Wheatstone has they have a few partners that have gear that works with Wheatstone's Wheatnet-IP. I'm not sure about Dante, but certainly Ravenna has partners that are signed on, including Lavo consoles, which now also work with Livewire. So without a standard, there become partnerships and people working together, but I can certainly see where a standard, as long as everybody can agree that the standard is healthy and good and doesn't penalize somebody because of their technology choice, or maybe they made a poor choice and they should go for the standard. But each company, Livewire, Wheatnet, Dante, AVB, Ravenna, each proponent believes that theirs is either better or best for some reason, something that maybe they came up with. There's the invented here syndrome, which certainly isn't bad. It's pride. Anyway, I just thought I'd speak to that for a moment about why these incompatible standards exist. But in the end, the marketplace demands, or at least wishes, for some commonality. So I can use this piece of gear with that piece of gear and have some promise that they will talk to each other and work together well. So there's your motivation, I guess, for X192 and that committee. So where did that committee get, and where are we going now?
Well, the committee actually wrapped up its work about 6 months ago. It's actually more like about 8 months ago. And it's been, it's funny for us. We feel like we've, delivered the baby, and now we're waiting for people to adopt it. And, that's what happened yesterday. So one of the, in the process, in the AES process, one of the things that can happen in this time period of the public comment is that if there's somebody out there in the world who, for whatever reason, wants to try to stop it, basically the negative approach, it is possible to get in there and through the procedures and everything, try to slow something down. So one of the pieces of information we know is that, there isn't any out there who really wanted to stop this. So that in itself, when you're coming from the inside out, there's many members. There were, it said 100 companies, signed up to X192. But yesterday was passing a critical threshold that says, there's no entrenched powers to be within the industry that really want to stop this. So it really bodes very well that this will be embraced and take off. And just as today, if you say to somebody, AES digital audio, everybody immediately has an idea what they mean. Now there's actually more than one. And of course, what we talk about as AES digital audio is AES3. So since then, we've gone from number 3 to number 67.
Okay, well, it's been a few years in between. So, okay, on the show, on past episodes, we've talked about how live IP audio works. So we've talked about the Livewire standard, and folks can certainly go look that up. And there may be papers available for Dante, and certainly there are for Ravenna, and maybe for Wheatnet-IP. When a standard like this gets approved, what's different than what? Of course, I'm very familiar with Livewire, and so are you. I think you've got a patent sitting on your desk that has to do with Livewire. What's different? What are the different companies going to have to architect differently in order to meet this standard? Did we lose Greg?
We did lose him. I'm gonna get him back.
Okay. All right. Hey, now's a good time to take a break and do a commercial for our sponsor, Axia. So let's go ahead and do that while we get Greg back. It's a good question, good place to leave hanging, because now that there's a standard, everybody's got to do some work. I guess Andrew's probably busy, so maybe he can't pop a website up. So maybe we ought to just take a break.
We're good.
Oh, you're good?
Yeah,
okay.
Go ahead.
Okay. All right. Our show is brought to you by This Week in Radio Tech, brought to you by Axia Audio, which was the founder of low latency live IP audio. And 10 years after folks at Axia started delivering the first systems, now we're moving toward this place where we have a standard where different companies will meet that standard, and different systems will talk to each other. But back when Axia and Livewire was a concept, we had to make a way for this to work. And so the folks at Axia, the scientists in Latvia, and here in the U.S. also, including Greg Shay, our guest, who's also the Chief Science Officer for the Telos Alliance, they worked to come up with a way to transmit very low latency, high quality audio over a local network. And a couple of chief ways they did that one way was synchronizing all the equipment on that network. So what we're doing there is we're synchronizing equipment to a very high standard, a very high clock standard, but we're doing it over essentially a jittery network. Even a local area network has some jitter to it. And so that's an interesting trick to do. There are certain techniques for doing that. When you plug your cable modem or your DSL modem into the network, you are synchronizing it over a somewhat jittery network. So we're doing the same thing, but just to a very higher standard. And then we had to figure out that packet size makes a big difference. So if we were to transmit very small packets that contained only a few microseconds worth of audio, then we could get audio delivered much more quickly at the expense of delivering a lot more packets. So, for example, Livewire, in its low latency mode, which is the usual way that we do it, each packet only has, I believe, it's 24 samples of audio, and it takes 2,000 packets every second to reassemble live stereo streamed audio from one place to another. 2,000 packets per second. So that's a whole lot more than, let's say, audio over the public internet, which may typically be more like 50 packets per second, or even less if the packets are really large. So that's something that Livewire had to do. Well, what does this make possible, this low latency? If you're not familiar with Axia and Livewire, check out the website, axiaaudio.com. And at the website, you can read about Livewire, read about why it was designed the way it was. We're going to find out in a few minutes from Greg what needs to change or be added to the Livewire standard to be compatible with AES67 and then a whole slew of other manufacturers' live streams. You can also read about our audio consoles. That's kind of how the thing got started, with the idea of having a networked audio console connected to networked audio sources and devices out there in your broadcast plant, and then tying all those things together with standard Ethernet switches. Now, they do need to be high-performance Ethernet switches, which is why Telos Axia recommends using Cisco switches. But tying all these things together, wiring becomes way easy. Configuring the system becomes extremely easy and fast. And the benefits just keep accruing. The more devices that you can just plug into the network that just work, and the less wiring and stripping of wires and punching down and soldering and just all that mess that you have to do, hey, the better. I had an interesting experience a couple weeks ago at a new facility here in Nashville that's owned by Cumulus. It's called Nash FM. It's a studio where they're producing a daily live morning show for the New York City market on Nash FM in New York City. And Blair Garner and some guests, regular hosts and guests, have a country music morning show there. Well, we had to add a profanity delay into the system, as you pretty much have to do on important shows that take phone callers or not. Anyway, we put a profanity delay in from the folks at 25/7, now part of the Telos Alliance. And there was no wiring to do. There was no audio wiring. There was no GPIO wiring. We plugged the thing into AC. We plugged in an Ethernet cable. We set the IP address. On the audio console, we set up a channel number for the GPIO to operate over and assign numbers to the audio streams. Bam, done. Now the lights on the console light up in accordance with the lights on the 25/7 program delay. The buttons on the console just make the program delay dump or pause or build back up or stop. It just works. It just works. And this is the beauty of when you have network devices. We hope to see that come to fruition for other manufacturers as well, as standards are built for things to interoperate. So that's what AES67 is about, and that's what Livewire got started about 10 years ago. On the web, axiaaudio.com. Check it out and read about it, and sure appreciate your consideration if it's time to buy an audio console or set up an audio router. You can do that with Axia gear. All right. You're watching or listening to This Week in Radio Tech, episode 183. We're talking about the AES Standard 67, just approved just in the last day or two. And this has come out of work done by the working group called X192. Our guest is Greg Shay, the Chief Science Officer at the Telos Alliance, and also our co-host, who I haven't let get a word in edgewise. I'm so sorry. Chris Tobin, the best-dressed engineer in radio. Hey, Chris. Chris, I'm sure
okay. No, Greg's talking the topics that people need to hear about and understand better. So I'll just sit back, and I have a few questions when the time is appropriate.
Well, good. Well, I asked a question before the break, and that was about what do manufacturers have to do, either generally or specifically now, to begin meeting this standard. And Greg, what are your thoughts about that?
Yeah, one of the changes is with respect to Livewire is Livewire invented, as you were mentioning, the synchronization mechanism, Murphy's Law, right? About a year and a half before what's called the IEEE 1588, which is an IEEE standard for precision time protocol and synchronizing down to as arbitrarily tight of a time sync as you want. Before that, everybody's often familiar with NTP, Network Time Protocol, which you can run a server, a daemon in your computer and keep your computer's clock accurate. Well, NTP is good to a couple of tens of milliseconds. We needed, and what we achieved with Livewire is we synchronized down to plus or minus 5 microseconds, which is a fraction of an audio sample. In other domains like machine control and all that, you also need precision time synchronization, and that on that basis, IEEE came up with this what's called the IEEE 1588. Although not specifically for audio, it can be used by audio. So AES67 uses 1588. Just like AVB. Kirk, one of the things we ought to address, you mentioned AVB, is how AVB relates to AES67. Really, from Livewire's point of view, there is the use of one of the headers, one of the values in the header of the packets, of the RTP audio packets, that we have to change sort of the definition of how we're using that. It was one of these things that was not clear in the original IETF spec. So that's a change. So, it's not tearing everything up and starting over. It's a little bit of change of the sync protocol and some details in the stream itself. So we were very fortunate. I think that comes from the fact that in Livewire, like I mentioned, from day one, we tested with QuickTime. We were focused on using existing standards, not inventing something or making something up, and that paid off in the end.
Okay. Now, you've mentioned several times this IEEE 1588 standard for clocking and synchronization, and you mentioned that it came along not too many months or a couple of years after we worked out in Livewire how to do clocking. But wasn't it, even though the standard was set, wasn't it some years later before the first equipment that actually produced such a clock was actually available and pretty expensive too? In other words, it really we didn't miss it by a few months. We missed it by a few years.
Sure,
it's good that we had what we had.
Yeah, certainly, and this has been a little bit of thorn in the side, also of the AVB people, that the IEEE 1588 time synchronization feature is not in your ordinary switch. It's not in even the enterprise class switch. As you know, we build radio studios out of what you would call the enterprise class, like Cisco switches, which are less than $1,000 for lots of ports. They're not generally the Soho $20 Ethernet switches don't handle multicast properly at all. So they're not generally usable. But this middle ground of enterprise class does. They have not adopted putting the IEEE 1588 time synchronization feature into it. The ones that you see today are typically very high-end switches or ones over in the industrial side used for factory automation. So, AES67 wishes that 1588 just becomes ubiquitous, and one of the things we have in our back pocket is, in the meantime, Livewire Sync works perfectly well, even without those special features. So we'll get there, and that's the answer to that.
Now, aside from this clocking, I remember that a few years ago, not too many years ago, we were having some pretty constant discussions with the guys at Ravenna. And Ravenna being invented after Livewire they had a lot of ideas for, I guess, maybe more flexibility, different applications, maybe even some tighter specs than Livewire, which we feel is perfectly applicable to what people need. So it still seems to me that there are things that Livewire, Wheatnet, Ravenna, and others have to do to meet this this AES67 spec. So maybe different audio formats or different bit depths, different sampling rates. What in terms of the audio, what will manufacturers have to do? And by the way, after that, we're going to have to talk about GPIO a little bit. That's a whole other subject. But in terms of the audio formats, what do people need to work toward?
Well, audio formats are actually one of the things that is a little bit easier, because linear 24-bit is has been part of IETF, the real-time streaming protocol. It's part of AES67. So that kind of falls on our lap. Interestingly, when you come down to how many samples you put per packet, I mean, in reality, it's not so hard to choose something, but one of the strategies in the X192 subcommittee was to realize, you have different choices, and to allow that, but the one number of samples per packet, so basically the packet size, was deliberately chosen to be one that nobody presently has. So just a little bit of a tip to say that, nobody gets a complete shoe-in without any work.
That's good. Okay. Everybody has to do a little bit of work here.
Yeah. And that was there was a little bit of that. They didn't want AES67 to basically come out just to be Livewire or just to be Ravenna, or one of the other ones. So I think the dynamics of the group were good, and were helped by the fact that as I mentioned, Kevin Gross, who was the inventor of CobraNet, was the leader of the group. And CobraNet was actually invented back in the early 90s, about 92, if I remember right, and was a real excellent piece of work, and actually worked on 10 base T networks with hubs. So this was even before Ethernet switches. And if you know how...
My goodness. Wow.
Yeah. Yeah, it's like so Kevin knows and knew that Ethernet technology moved on, and, you know, to credit to him, wasn't trying to make AES67, you know, basically push CobraNet on everybody. So he was not only knowledgeable enough to understand what you really should do in light of the more modern network technologies, but was kind of like the guy in the middle who, you know, of course, everybody has a stake in the game, but, you know, between the other players, Livewire and Ravenna and Dante and all, and AVB, Kevin was really the guy who was focused on, let's find, you know, a good neutral ground that isn't going to start any fights and make it seem like, you know, hey, you know, this is slanted one way or the other.
Gotcha. All right. All right. So I was looking, we have this document. I'm holding it up right here. Let's see if Andrew will switch my camera to me here. Hello. Hello. This is called the Standards and Information Documents, AES Standards for Audio Applications of Networks, High Performance Streaming, Audio over IP Interoperability. So this is a document from the AES. If you're an AES member, this document is available free to you. Just look up AES67. And you can go through the, you have to check out anyway and pay $0, but you can get this document if you're an AES member. If you're a non-member, I think it's $50, so you may not you know, need it, and if you might as well become an AES member for about that much money. So this document, Greg, looks to me like a lot of the document just simply goes through explaining, you know, the different standards that come together. Things that we use almost every day anyway, references made to things like Ethernet, end-to-end transparent clock, DSCP, diffserv, even byte is defined here. So even though the document's almost 50 pages long, one part of the document that I was really interested in is this concept called link offset. There's a diagram showing link offset. Can you kind of help me understand what that means?
Okay. Well, you're asking the right guy. For better or for worse, that terminology came from me. And what I was trying to do is avoid overuse of the word latency. You know, if I said network latency to you, that can mean a lot of different things. So what we needed is a specific, term that what you have to do is be aware of how long the you know, the time delay is for, like, basically one hop over the network. So and you have to know this and basically configure your equipment. You know, whether your network is running you know, fast or slow. It's a configuration parameter. Other ways it shows up, if you're familiar with configuring like the Axia nodes today, there are default buffer settings, but under the standard streams you can go in and set the amount of buffering that you want at the receiver. That's another point of view of the same parameter. You got to know how well your network is performing, and then you set the link offset into the equipment as a compensating factor for the timing of the network.
Oh,
so
okay.
It was deliberately chosen as a little bit of a new term to avoid the confusion of, you know, the eighth use of the word latency.
Yeah. Okay. All right. Well, Eskimos have what, 8 words for snow because
there
it's
you
important
go.
to them. So we have to differentiate this. Now, tell me, you know, in an Axia Livewire network, your source of clock can be automatically chosen from almost any hardware device on the network. How does the source of clock differ in an AES67 network setup, or does it have to differ from that?
Well, sure. This falls into the umbrella of the IEEE 1588, and that that system has a similar mechanism that if you have a bunch of peers, they each have knowledge of how good of a clock they are, and when it comes time that they have to elect who's going to be a clock, the one with the best quality. In fact, IEEE 1588 is quite more sophisticated, and you can know things like not only am I an accurate clock with a good crystal, but I am referenced to an atomic clock is actually there, or a GPS source. So it's very well thought out, and where we took some first steps functionally to solve the problem for synchronization of the audio network with Livewire. IEEE 1588 solves it for any sort of time synchronization that you could want, including automatic handover, failover, redundant masters, different qualities of masters, so on and so forth.
I noticed that with Livewire, we talk pretty much exclusively about multicast IP audio streams and how we let the Ethernet switch that's multicast aware and capable do the heavy lifting with regard to duplicating streams for the purpose of various devices that have requested them. I noticed that the AES67 standard calls for both multicast session descriptions and unicast session descriptions. How and when would you use either multicast versus unicast?
Sure, and that was a key part of AES67. Is this comes from the philosophy that you can think of an audio network as being inside the studio, and the key value of multicast is that all of your audio channels are available everywhere. If you go into a room and you're trying to pick up that satellite feed that came into the operations center, you can pull that up on your board in this room. You don't have to go and configure any other piece of equipment, somewhere else, essentially where the satellite feed came in. So that was always very key to how, radio stations run, when always at the moment you are deciding what you want to, I froze there for a moment. In the moment, figure out what audio comes out where.
Gotcha.
As soon as you go outside the studio, the fact of the world is that expanded either enterprise networks, some of these corporate networks, like Clear Channel along their backbones, or WANs. And what's happening nowadays are these essentially these private WANs that the telcos will create for you. Mm-hmm. For whatever reason, multicast is not as well supported. So either they don't want to deal with it, or they don't want to manage it, or whatever. So in recognition of that, typically whenever you want to go outside the studio facility, it's often more convenient to go unicast. And this is just the natural evolution, and that was recognized in AES67, and it's kind of one of the key links that in the future is going to allow tying of audio in the studio to outside the studio.
There's a section here, section 9 is called Discovery. What's meant by discovery? And I to me, if I think I know what it is, discovery is one of these things that right now is definitely not interoperable between different companies, different standards. What's discovery?
Sure. Discovery is the process of finding out what audio streams are around. So if you use Axia equipment, you're familiar with the front panel of the router selector, where you have a list of all the channels that are around. Or when you're configuring the destinations in a node, you hit the little icon and you get this list. So it's the directory. It's the index.
Okay.
As soon as you have thousands of channels, it's like the TV guide, on your cable TV, if anybody actually watches cable TV anymore.
Okay.
In fact, I keep looking for where is the, the program index for all these various services like Netflix and Hulu and all that. If you had a website that you could go to that would allow you to see, across all the different services that were bringing and YouTube, fine, that would be discovery. And you're right. If you look at the AES67 document, discovery is not standardized. And this was a lot of discussion, one of the contentious things, because one of the points of view is, like I just mentioned, and we've seen this. We build these big facilities. Radio Free Europe has 3,000 channels of audio around. What are you going to do? Memorize all the channel numbers, for all that? What's where? So, in real practical day-to-day operations of a modern radio facility, that keeping track of what's where and essentially the phone book, is pretty key. So some of the members of the committee felt strongly that it should be included, because you make this big multi-channel system and then it becomes hard to use. What are you accomplishing? But other members of the committee felt strongly that, let's not try to solve all the problems at once. Let's not overspecify this, leave the door open. Let's do this in layers. So AES67 is the audio streaming layer, how you get the audio channels hooked up, not trying to solve all the problems yet. So there's the door open there for future work, but it's the layered approach. So as a for instance, as you would have in the not too near future, in the not too distant future, Axia equipment that you'll put into AES67, audio stream mode, you'll still have the familiar, Livewire product lists of channels and things to choose what it is you want to connect. So that's the discovery part.
Gotcha. And I see in Appendix or Annex E of this document, we have listed the discovery methods used by a couple manufacturers and some generalized ones, including Bonjour, SAP. SAP, is that Session Announcement Protocol? Is that what that stands for? Oh, wow, I guessed. There's also Axia Discovery Protocol, which is listed here, and Wheatnet-IP Discovery Protocol. So there are some listed here, and these are the systems that are out there now. Certainly an IP audio system can work without a discovery protocol, but man, would it be tough to set up. You'd have to separately keep lists and stuff, and with a discovery protocol built in, you've got this, you hit a button, you got a nice list of all the channels that you could, route to this location, and so that it works well. I understand why they didn't want to bite off more than they could chew here and specify a protocol. I guess at some point manufacturers may, to some degree implement other people's protocols. Who knows, but that would be nice. So, hey, I mentioned about GPIO. We ought to chat about that for a minute. What is happening in that world? Because if you're in broadcast, I got to tell you, GPIO is almost as important as the audio. Now, in the recording studios and live sound, you probably don't have GPIO or very little of it. But I tell you what, in the broadcast radio station, you need to know when stuff happens. You need to be able to push a button and have something happen at the other end easily and without a whole separate wiring infrastructure scheme. So doing that over the the same Ethernet that's handling the audio, is really convenient. Where's that going to go?
Okay, as you said, that is very important and was recognized, was talked about, and like I mentioned, at least in terms of the context of where we were in this AES subcommittee talking about the audio streaming and audio streaming interoperability, we knew that over in the next room were the X210 guys. So there's an AES. Okay. Yeah. X210 is putting a AES standardization on what's called OCA, Open Control Alliance, if I haven't cited that wrong. And that is specifically their focus. So we weren't about to try to muddy the waters between there. And so it is very, very much recognized. And, as standards go, get it out there written, and then build the coalition of people who actually, use it. So that is work underway.
So, okay, my point of view here, I'm coming from the perspective of an Axia user. in Axia, it's easy to correlate an audio stream with its associated GPIO or contact closure or control mechanism. Here in AES67, there's no mention of GPIO. That's a separate committee. So they come out, let's say at some time later, they come out with recommendations or a standard for control and machine control and such. Is there a way for these two standards to be used together then, or would that be up to each manufacturer to associate a stream with a GPI with an X210 protocol?
That's a really good question, Kirk. I think in a year maybe I'd have an answer for you, but we are all a little bit of wait and see. One of the principles at work here is, this is a general principle of IP networks, in that you build in layers. So just because you don't have the GPIO, bundled into the audio streaming, doesn't mean that at, a higher layer, in other words, all you basically need would be the address of that device, and in some implementations of audio streaming, you literally address the audio stream like with an HTTP address. So it's certainly possible that in the future that given that one object address, which would be the device, then underneath it you talk to it with both control and audio, and you get this integration that you're after. Got you. Okay. All right. Well, our hour is going to draw to a close in a few minutes, and Chris Tobin has been eagerly standing by. He's familiar with Axia and Livewire, and presumably, Chris, you're familiar with, generally speaking, other protocols as well, since your work is pretty wide ranging. What do you want to ask Greg about where this AES67 will take us?
Well, I'm curious, since we're talking interoperability, and from the days of ISD and NT1, all kinds of interoperability exist in some levels. Do you think this is the first step with AES67 to sort of get everybody on the same page and realize, as you said earlier, as the tide rises, all the boats rise with it, that this might be a way for all the competing market dynamics of manufacturers and business heads to say, okay, you know what, we'll agree to work at a certain level and then make things happen and let the user, the end user, dictate which is the better of the better class, because we decide as manufacturers to find features that the end user wants more of. So whether it's an Axia, Wheatnet, Dante, Ravenna, that's okay, it doesn't matter anymore. Now it's about the surface. This surface from this manufacturer does much better than what I want, but I like the way this protocol works, and sort of they try to do a mix and match. You think that's something on the roadmap down ways out? As Kirk was asking about GPIOs, I'm just thinking even a larger picture. Yeah, I think that's precisely the point, and that is very true. As I had mentioned, we make a lot of different kinds of gear, and we fully expect that people would choose our equipment for the features, other than the fact that it can communicate using networked audio. That we're happy to see the networked audio become a more generic spigot on the back, and there's going to be companies who make features and functions that where we don't, or people may prefer, and so it's important that stuff plugged together. Exactly. Well, the reason I was asking is, in part, in my past, I've worked for two major radio network distribution facilities, Earth Station uplinking and network distribution. And one of the biggest problems we had at the affiliate level was the interoperability between our delivery systems and interconnectivity and theirs. And now that we've moved, we fast forward to the world of IP, and suddenly everything becomes very ubiquitous in its gray area. Back in the days, you had a satellite receiver, the output went into a standard, audio routing switcher matrix, end of story. Now it's packets that could be anywhere from any device. So I'm a network operator. I would say standardize on Axia for my distribution internally. But now I've got several hundred affiliates who are a mixed bag of other systems. So this would be a way for the business models to shift, and now all of a sudden give advantageous, market opportunities for the end user, along with manufacturers who are smart in their delivery of design and form and function. Would you, AES67 look like it's going to help to go in that direction too?
Yes, that's exactly what it's aimed for, and that's exactly why it was named an interoperability standard. As you know, like with some of the ways that the MPEG audio compression standard was written, MPEG doesn't tell you how to do it. It doesn't tell you that you have to build it this way. It's just saying that, at the end of the day, when what you output has to conform to this for the purpose of interoperability. So, yeah, it's along those lines, and in a lot of cases, it was a matter of just writing down. You write down the list of what everybody agrees to use. And Kirk, you mentioned that if you actually look at the AES67 spec, remember on the first paragraph that you read, it was a stated intention not to invent anything. So really it is an exercise in collecting together all of these existing protocols and simply saying, you have this toolbox with, n infinity degrees of freedom, so let's pick this set of how we're going to use this toolbox so that we can all talk to each other.
Okay, so this brings a question for me. There's another standard out there that codec manufacturers try to adhere to called NASIP or NASIP or Network ASIP. And in my humble opinion, if you're going to buy an IP codec, you ought to buy one that says it complies with NASIP. However, the standard, I think, is terribly lacking. It absolutely assumes that your IP path is absolutely perfect. It assumes there's no problem with that. And so in a way, I'm not going to say it's a useless standard. I just don't see a whole lot of benefit. It barely helps different codecs talk to each other. And if there's any trouble between them, well, things just ain't going to work out. I guess what I'm asking is, does AES67 in some way represent the same potential for problem? Hey, we meet 67. Hey, we meet 67, but the two still don't talk to each other. Could that happen?
If you're talking about network technology, I think we've proved through 10 years of Livewire, Livewire does assume that the network is essentially loss-free. There was a lot of worry about, well, what do you do about out-of-order packets, missed packets, so on and so forth. The reality of enterprise networking is that, there's hundreds, thousands, millions, billions of packets with very, very low errors, below the threshold where, if you were to hear a tick or a click or a pop, once a week or something, if you were listening for it, it's acceptable for the use of the audio studio. So kind of what you're putting your finger on is how mature is network technology? How valid is this assumption of a good network? AES67 does assume the network does a good job. The longer distance, and as soon as you get the internet involved, of course, is a whole different story. Yeah. So AES67 is not about internet audio at all.
Well, maybe I was asking the question, framing the question incorrectly. I wasn't really asking it. I know that the problems might be different. I don't think that when the people who were working on NASIP, that they expected there to I guess it seems as though the NASIP standard is so broad that and there's some plug fests that go on to test things together, but the plug fests all happen on the same LAN in the same room. And yet with NASIP, you can have two codecs that are NASIP compatible and yet still get a less than ideal connection between them, because both codecs are kind of operating in a stupid mode. In other words, they're just plain dumb codecs at that point with no manufacturer proprietary stuff going on. Could AES67 become the same way? That, well, yeah, we're compliant, and yet why is it that we they're always talking at the lowest level, or there's always stutter or jitter? I don't know. Maybe we can't see the problems that might come along. Maybe I'm worried over nothing. But I'm just wondering if the standard is tight enough so that the things actually will work together from an audio point of view.
Well, I have a good answer for that, and that is we were very fortunate in this respect that we partnered with Ravenna just a couple of years, before this X192, the AES67 work started. So the proof in the pudding, if you will, of the practicality of different manufacturers getting together and talking has really been demonstrated by how we, successfully interoperate with Ravenna and them with us. So it's I understand where you're coming from. Whenever you're into the gray zone, you hold your breath, and is the audio going to be broken up? But we've proved it to ourselves over 10 years and shown with Ravenna that the interoperability works. So it's not that much different. And based on that, I have a very high degree of confidence that there aren't going to be any nasty surprises.
Gotcha. All right. Well, we're out of time, and I told you an hour would fly by, and it certainly has. Greg, I appreciate so much you being with us. Chris Tobin, thank you for adding your salient questions there at the end of the show. I appreciate that very much. Would Greg, maybe you'd like to wrap it up with telling us or giving us a view of when we might expect to see AES67 products become a reality, and at what point do you suspect that something from Axia might work with something from Dante or Wheatnet?
Well, certainly next up on the activities is the first AES67 Plug Fest is being organized. I don't have a date for that. I think Livewire and Ravenna equipment in AES67 mode is going to happen pretty easily in terms of the teams are already working together. But our X nodes, our second generation audio nodes, were designed specifically to allow for everything that AES67 may have turned out to be. So we're ready and to deliver on that, and it's I guess it's a matter for some of the other guys to step up too.
I'd be eager to hear about this Plugfest details, but usually these Plugfests occur in Munich around Oktoberfest time, don't they? Are the results really accurate?
I think that's this week or next week, so that would be a mighty short schedule.
Hey, Chris Tobin, the best-dressed engineer in radio in Manhattan, thank you for being with us.
Oh, you're welcome. And you know what? With IP, Kirk, you're going to have people that won't be able to figure it out right, and the two endpoints will still have issues, whether it's NASIP, Livewire, Wheatnet, Dante, or Ravenna. I've been running into some issues already with people.
Yeah. Well, that's my fear.
Process.
That's my fear, but there's motivation to make these things work together. It may not be directly identifiable motivation, but overall, from a business standpoint, there's motivation. And so,
hey, Kirk, can I inject one last point?
Please.
I wanted to get back to the AVB point.
Oh,
The other very established group is the AVB group, which is also Avenue, is the consortium of vendors. And the way to understand AVB is layer 2, which is where Ethernet lives. AES67 is layer 3, which is routable and extendable for wider distances. We are very interested, those on the AES committee, we're very interested in the fact, and for instance, the synchronization was specifically mentioned. If you look at that document, one of the ways that the synchronization is called out is not only by calling it IEEE 1588, but also 802.1 AS, which is an AVB.
Yeah.
So
that's what AVB is. Okay.
So what we look toward is, we know in some cases, for instance, inside an automobile, hey, Ethernet is all you need. You don't need to necessarily route anything in the car, out of the car.
Right.
But therefore, for instance, broadcast studio, you do need to connect with the outside world. You do need layer 3. You do need to be able to route. So what the hope is that as the AVB people need and realize they want to have a layer 3 solution, that they use AES67. And so there's that desire there that it's also a link for the AVB equipment as they move up to layer 3.
Interesting. Okay. Well, it looks like AES67 does have plenty of application and for disciplines outside of radio studios, and it even mentioned live sound and other recording applications. So wide adoption could be a very good thing for us all. Greg, thank you for taking your time to be with us. Greg Shay is the chief science officer at the Telos Alliance. Appreciate you taking an hour out of your busy day to be with us, Greg. Thank you.
Sure. Thank you, Kirk.
And Chris Tobin, thank you once again for being with us on the show, taking an hour out of your busy day from Manhattan. And by the way, I'll be in the city in a little over a week, so maybe we can
Excellent.
We can get together real quick.
Over a little week. What dates roughly?
I think the 21st, 22nd.
Oh, good. Yeah, I'm traveling on the 25th, so perfect. Yeah, perfect.
Okay. All right. Well, I'll give you a holler. Hey, thank you, Andrew Zarian, for producing and switching the show. Thank you very much for also making the GFQ network available for This Week in Radio Tech to have distribution far and wide around the world. Appreciate the great exposure and also the professional way you make us look. Thanks very much. That's it. Our show's been sponsored by Axia Audio on the web at axiaaudio.com. We'll see you next week on This Week in Radio Tech. Bye-bye, everybody.
That's all the bandwidth we can pill for this week. Another tort has propagated, and all the transmitters and audio equipment live happily ever after, thanks to the handsome engineer and his kind, benevolent care. We'll be back next week.
Lord willing and the creek don't rise.
This Week in Radio Tech. Subscribe to iTunes and you'll never miss a show. Search for This Week in Radio Tech in the iTunes Store. Soliciting is strictly encouraged. If you liked today's show, tell a friend. If you didn't like it, we were never here. Kirk Harnack's wardrobe provided by the Salvation Army and the Red Cross Disaster Relief Services. Hair and makeup provided by Penelope Garcia Hernandez Weinberg.
He's unique, wouldn't you say?
I just want to get it over with.
This ends this transmission. Tango, Whiskey, India, Romeo, Tango. Signing off. Okay.